GCSE Physics Boosters. This video is about sound. Sound not necessarily in air, but sound traveling through solids, as we shall see. Now remember, sound is a longitudinal wave. There are transverse waves and longitudinal waves. What does that mean? What does longitudinal mean? You should remember that. Okay, so when a sound wave traveling in air meets a solid, then it may be transmitted through the solid. In other words, the sound makes the solid vibrate, and then the vibrations travel through the solid. Now, this is a picture of somebody's ear, and basically what happens is the sound comes through the pinna, which is the outer ear, and then you've got the eardrum, which is this membrane, and that vibrates. So this is an example of sound waves traveling through the air, and they meet something solid, and then the sound wave travels through the solid, and the particles in the solid will vibrate at the same frequency. Now this isn't a biology exam, but a little bit about how the ear works. So the sound waves enter the ear, and they make the eardrum vibrate at the same frequency. Then inside the ear, in the middle ear, you've got these tiny little bones, the hammer and anvil and stirrup, the ossicles, and they vibrate as well, and they amplify the vibrations. And then the vibrations are passed on to this thing that looks a bit like the shell of a snail called the cochlea. And inside the cochlea, there's liquid and lots of tiny little hairs which vibrate at different frequencies. And they are receptors. In biology, you'll learn about receptors. They produce electrical signals that travel to the brain through the auditory nerve. Okay, so it's a little bit about how the ear works. Basically, vibrations of sound in the air travel through solids, and this produces an electrical signal in the cochlea. Something you need to know, the range of normal human hearing is from about 20 hertz to 20 kilohertz. As you get older, that 20 kilohertz kind of gets less and less. Okay. But that's the range of normal human hearing, 20 to 20 kilohertz. Remember that. This is higher than that. This is an ultrasound scan. Now, ultrasound is basically anything above 20 kilohertz. It's sound that we can't hear, that humans can't hear. Now, in an ultrasound scan like this is prenatal scanning, looking at an unborn child or a fetus. They're used from about 2 to 18 megahertz, so very high frequency sound. And the way that it works is that these waves partially reflect off the boundaries between different tissues. Different tissues as in skin or muscle or bone that's forming, or cartilage. Different types of tissue, the boundaries between them, that's where the waves reflect. Then these reflected waves are detected. That this doctor or nurse is holding a thing called a transducer, and that's giving off the waves, and it's also detecting the waves. And from the time it takes for the waves to get there and back, a computer can work out how far they've traveled, and it can build up an image of the unborn baby. Interestingly, they always put loads of jelly on the mother's tummy, and that's to reduce the amount of reflection at the skin, at the mother's skin, because that would confuse the signal a great deal. Ultrasound or ultrasonic scanning is used in industry to look for, to detect flaws, for example, cracks. I mean, this might be something like the wing of an aeroplane. and you need to look inside it, look inside the metal, or look inside a pipe to see if there's any cracks. So any kind of flaws, any kind of defects. And basically what happens is that the ultrasound will reflect off the crack. And then again, a computer can build up an image and you can actually see inside the metal. Okay. If you look at the trace here, if I can bring a pen up. Okay, so that's the original pulse, ultrasound pulse. That is the reflection of kind of the wave that's gone there and back again. Okay, and this one here has taken less time. And the reason it's taken less time is because it hasn't traveled as far. I mean, it's a bit cleverer than that, but basically this machine, you can look for cracks and defects inside components. This is another typical kind of sound thing, sonar or echo sounding. Echo sounding using high frequency sound waves, and fishermen very often use it to find fish, to look for schools of fish, or to explore the seabed, to look for wrecks and things. Okay, in fact, I think most fishermen have this now, sonar, echo sounding. Lastly is earthquake waves. Now, an earthquake is caused by kind of tectonic movements, like a couple of tectonic plates rubbing against each other, and they move very quickly, and this produces lots and lots of waves. It produces two types of wave that we need to know about, P waves and S waves. Now, what's the difference between P waves and S waves? Well, P waves, now you need to learn this, P waves are longitudinal. Remember, P is push. P waves are push. S waves are transverse. So S is shake. P is push. S is shake. P waves are faster. S waves are slower. That's easy to remember. Yeah, S is shake and S is slower. And then P waves can travel through solids and liquids, but S waves can't travel through liquids. Okay, transverse waves can't travel through a liquid, only longitudinal waves. This picture at the bottom here is a seismograph, and notice that the P waves are detected first. Why is that? And if you don't know, look at the information above. You should be able to figure that one out. On the surface of the Earth, there are lots and lots of seismometers, hundreds of seismometers detecting earthquake waves. Now, when an earthquake happens, it produces P and S waves, and they behave very differently. Now, one thing to notice is that the waves curve, if you look at that, and that's because as you get deeper into the Earth, the density changes. And when there's a change in density, then you get refraction. And if you don't know what refraction is, we'll cover that in another video. So the waves curve as they go deeper and deeper into the Earth. Now, when the waves reach a sudden change in density, then there's a lot of refraction takes place. Now, what will happen to the P waves? First of all, the P waves, these P waves will come along and they'll get to here. Now the P waves next to them, when they get to here, they're going to refract and do something like this. Because there's a sudden change in density, as you go from the mantle to the outer core, they refract quite a bit. And then when they leave the outer core, they refract again and they get to there. And what you end up with is here, it's called a P shadow. There are no P waves here. So you've got P waves coming here, then the P waves next to them here, they do a big change of direction there and there. And so you get P waves here and here. These P waves here have actually gone through the Earth's core. They've gone through the outer core and the inner core. Okay. Now I'm going to change color and talk about the S waves. So the S waves, first of all, they'll do something similar up to here. So around here, we'll get lots of S waves. Notice that their path is curved as well, but they won't get through the outer core. And why not? Because the outer core is liquid. So you only get S waves, I think it's about, I've seen different values. I think it's about 110 degrees. That angle is about 110 degrees. And then you don't get any S waves down the bottom there. Okay. Now, the point is that if you pick up all these P and S waves with your seismometers, you can actually figure out what's going on inside the Earth. This is how we know the structure of the Earth. We know that the Earth has a mantle and an outer core and an inner core from detecting P and S waves whenever an earthquake happens.